Hello, class of physics 2. Actually, the contents will be theory of special relativity, and this is a part of modern physics. And these are the actually contents we have to cover up for this chapter: frame of reference and its classification, postulates of a special theory of relativity, the Lorentz transformation and its inverse, Galileo transformation and limitations, length contraction and time dilation, relativistic momentum, relativistic Newton's second law, work done, mass and energy equation, and momentum variants. And we also discuss a very interesting example of theory of relativity, special theory of relativity, twin paradox, and the resolution. So I hope everybody will concentrate on this. Okay, first of all, what is relativity about? Actually, the relativity, there are actually two kinds of relativity theory, special and general, both created by Einstein. Today, we'll concentrate almost entirely on special theory of relativity. Why do we need special relativity? Well, here at an Fermi lab, we accelerate particles to every nearly to the speed of light. Special relativity allows us to describe what happens at very high energies. Fundamentally, both special and general theories of relativity deals with the concept of space and time. So it is curious to see how our understanding of space and time evolved through the history. First of all, in historical notes, Aristotle views on space, time, and motion were very intuitive. They're pretty much how people feel about these things. Here are the Aristotle's views on space and time. Every sensible body is by the nature somewhere. And this is the physics. This is the example from the physics. Time is the numeration of the continuous movement. This is actually before placed idea. Now, Aristotle's space and time, this is actually x, y, and z. There is three-dimensional coordinate system. If you place a clock on origin, then there exists a prime mover, privileged being the state of absolute rest. The position of everything is else measured from the three numbers x, y, z. You must know three-dimensional coordinate system x, y, z with respect to the prime mover who sits at origin. That means from 0, 0. Okay, origin. The time is measured by looking at the prime mover clock. Actually, this point of view prevailed for almost 2,000 years. And Galileo's challenge, Galileo argued that there is no such thing as absolute rest in his view. The mechanical laws of physics are the same for every observer moving with a constant speed along a straight line. This is called inertial observer for short. That means we are inertial observer or inertial reference system. So this is actually Galileo's point of view. And Galileo's space and time also same as the Aristotle, but a little bit different. Every inertial observer could declare themselves the prime mover, the measure position of everything with respect to their own set of XYZ. The time is still measured by looking at the prime movers. That means same as the Aristotle's view. And this is the Galileo's transformation. So who have two frames of reference K and K dash. There are two types of reference. K and K dash is moving along axis Y with same this. That means there are another dimension T time will be added. So this is 4-dimensional XYZ. So if any objects moving along the Y axis, then they are a little bit distance bt, velocity multiplied time will be added along the y-axis. This is the point from the Galileo transformation. And this is the Newton's law of mechanics. Newton's law of mechanics. The Newton's law of mechanics are agreement with Galileo's relativity. A body not acted upon any force stay at rest or remains in uniform motion, whichever it was doing to begin with. That means another two. Number two, to get the an object to change its velocity, we need a force. That means force multiply mass multiply with product with the acceleration. That means acceleration equals to what? Change in the non-uniform velocity. Rate of change of in non-uniform velocity. So force can be written down in mathematically ma, mass and acceleration multiplied. So this now Newton's laws are the same in all inertial frames. Okay, according to the Galileo's transformation. So we must know if we change velocity along y-axis with respect to time, then we get y equals to y dash plus bt. Y dash means the initial uh, distance along y-axis. Now here comes with Maxwell. Actually, Maxwell brought it together the knowledge of electricity and magnetism known in his day in a set of four elegant equations known as Maxwell's equations. In the process, he introduced a new concept of electromagnetic waves and found that traveled at the speed of light. Light is an electromagnetic phenomenon. So this is the concept from James C. Maxwell. So electromagnetic waves, this is the actually figure of magnetic field and electric field. So magnetic field and electric field coincides in orthogonally, and that means a 90-degree angle. So this is the, and waves in general like this. The waves are, we are all familiar with, the require something to propagate in. That means sound, you are hearing my sound in my lecture. This is the waves are compressions of air. So spring compressions in a shinky in second one. So what about light? The most natural assumption would be that it requires a medium too. So ether, this is the very important properties of light. This mysterious medium for a light was called ether. So what would be its properties be? And you must know about the ether, and Michelson Morley experiment shows this the existence of ether. That means to detect ether by measuring the speed of light in two different detections, upwind and downwind with respect to ether. So Michelson Morley experiment. This is the short description of Michelson Morley, who have confirmed that there is no ether or an error in the same measurements. So this is the and real life example for the electromagnetism governed by the same rules of Newtonian mechanics. The addition of velocities, okay, addition of velocity along y-axis, ui equals to ui dash plus b. Another b means what? Actually, if we consider this b as the same as the speed of light, that means c, then we get this assumption. So now we know from this that Newton's mechanics based on Galileo's relativity and Maxwell's will be electrodynamics. So the fact that there is such a constraint is consistent with the Newton's mechanics. So Einstein's choice now in 1905, Einstein was faced with the following choices. The Maxwell's equations are wrong. The right ones would be consistent with Galileo's relativity, and it's unlikely Maxwell's theory has been so well confirmed by numerous experiments. Galileo's relativity was wrong when applied to electromagnetic phenomena. There was a special reference frame of light, and this was more likely, but it is assumed the light was like any other waves and required a medium for propagation. That medium was not found. So there is a relativity principle for both mechanical and electromagnetic phenomena, but it is not Galileo's relativity. So this is from the concept from the Einstein. So Einstein's relativity postulates it is required the genius and the courage of Einstein's to accept the third alternative. His special relativity is based on two postulates. That means first postulates all laws of nature are the same in all inertial frames. This is really a Galileo's relativity. That means he is accepting um, postulates from Galileo's, and another postulates. Second postulates the speed of light is independent of the motion of its source. That means this simple statement requires a truly radical rethinking about the nature of space and time. So these two postulates makes another part of relativity, which is called the special theory of relativity. So now, now we want to explore the essence of special relativity, which is our main topics of this class. From the point of view of Einstein, what is time and what is space? So actually, if we think about this, it's a common sense. If someone is running from left to right on a straight line, actually the velocity will be added. So it's common sense. We can imagine the speed with respect to u is 4 meter per hour, mile per hour. Actually, someone is running. Suppose you are running uh, from the initial uh, point to another point. That means with velocity will be 4 mile per hour. So suppose the speed with respect to you, that means your own speed and another speed. That means you are running with 2 mile per hour. Uh, you are running in a vehicle or any other or with air. Okay, then that means the velocity will be added. So total velocity will be 4 mile per hour. Now the speed of ball is greater for toss 1, toss 2, and toss 3. Car moves while a passenger tosses a ball, right? The experiment says the speed of first ball, is the fastest, just like at the airport. Suppose you are traveling with a car, then if car moves while a passenger while you are tossing the ball, that means the first ball will be the fastest from this experiment. That means the speed of ball is greater for the first one. Now, the speed of light is greater for first beam, second beam, and third beam. If the car moves while a passenger shines a flashlight, then the experiment says the speed of light is the same in all directions. That means if this seems to be the light will be with the same velocity. Okay. Now you are worried of what does it mean for the real world? Enter the main Einstein. So the Einstein thought experiment. Consider a beam of light that is emitted from the floor of a train that bounces off a mirror on the ceiling and returns to the point on the floor where it was emitted. That means the velocity will be b. Okay. So in that case, the Einstein's thought this experiment where emitting the light. So the light is emitted and detected at the point A. This fact must be true no matter who makes the measurement. So Sam is on the train. Suppose someone is the name Sam, the man on the train. So the velocity of light will be c, and c means what distance by time. So c equals to 2 is divided by, that means time of Sam. So time of Sam will be twice is divided by c. So if he travels from the bottom to top, the distance will be ace. So if he travel from this point to top and again return to the initial point, then the distance will be 2 ace. This is why Sam's time will be taken what? 2 h divided by c. So Sally, another one, watches the train pass and makes the same measurement. So the light is emitted um, from the same distance. So if we take this, the light will be, Sally is standing still, so it takes 2 clocks. Okay, Sally 1 and Sally 2, there will be 2 clock. In first clock, light is emitted, and in the with the second clock, light is received. So from Sally's point of view, path light takes to mirror. Okay, and path light takes from mirror to detector. The same with the same distance, the distance train travel while light is traveling, b multiply capital T Sally. So the distance will be root of RS square plus b by 2 multiply total time taken by Sally whole square. Makes use of Pythagorean theorem. Actually, we can get this one by using Pythagoras theorem. So from Sally's point of view, uh, velocity of light equals to distance by time. This will be given by twice d divided by capital T of time taken by Sally. So time taken by Sally equals to twice d. That means total travel distance divided by velocity of light. So same on train and same on ground, there are two types of velocity from point of view of Sam and Sally. So we get actually two types of equation from here. Now, actually, we can get a time dilation equation. Actually, try to um, determine the and evaluate later. So think about this. What is the so special about the light? Nothing, everything acts in this way. Time is not absolute, it is relative. So can this be experiment true? Experiment says yes. So suppose there are two types of clock. One is in ground and another one is in plane. So there are two types of clock. We are measuring time. Now suppose the another clock in at the space craft and another is one in ground. So less time elapsed on the clock carried on the airplane. That means we are observing this after traveling, the less time elapsed on the clock carried on the airplane. So if you calculate with that equation, we get how long does person appear to live in storm on Earth. Actually, the measures the length of a box car where you are in on the car, and in second figure measures the length of a box car moving you by you. So there are two types of length with the velocity b. The length is relative to. That means if the velocity b is equal to 0, then length large velocity. So if we take the two length, we get the length is relative. Now, very important transformation after Galileo's transformation, the Lorentz transformation, the same as we get the three-dimensional space events at x, y, z, t. T is the fourth dimension, time. Now, Lorentz, after a transformation, we get x dash, y dash, z dash, and t dash after an event happening. So Lorentz transformation says, why is this vitally important for science and as a whole and physics as a particular? How are x, y, z related to x dash, y dash, z dash, t dash? Actually, after the initial frame, we get the interference x, y, z, t. After the transform by Lorentz transformation, we get the transformed equation will be this. So in Lorentz transformation, we get the actually space and time get all mixed up when you relate observations made from different point of view. That means the length along the x-axis and y-axis and z-axis will be invariants, but time will be different. Time dimension will be changed. All other things that can be observed must be a relativistic transformation too. So mass, momentum, P equals to mv can be transformed to E equals to mc square. That means energy can be transformed to mass multiply velocity of light whole square. So now today we'll start this class. This is actually a brief presentation of theory of relativity. So now, first of all, what is the actually inertial frames and non-inertial frames? The frame with respect to which an unaccelerated body appears or the unaccelerated are called inertial frames. And in other words, the frame which are at rest or in uniform translatory motion relative to one another are called inertial frames. So what will be the non-inertial frames? The frames, non-inertial will be the frames, the frames, the frames relative to which, relative to which, relative to which an unaccelerated, an unaccelerated, accelerated body appears accelerated are called non-uniform, non-inertial frames. So actually, suppose this is the x and this is the y and this is the z. If any body is staying at rest or in non-uniform motion, then it is called inertial frame. But the frames which is relative to which an accelerated body appears to be accelerated, then it will be called non-uniform or non-inertial frames. Now the important definition, what is reference system? A system of coordinate axis, a system coordinate axis relative to which the motion of an object is described is called a frame of reference. That means we can define also what is the frame of reference like this also. Thus, a frame of reference is a system of coordinate axes which define the position of a particle or an event in two or more or three-dimensional space. The simplest frame of reference is the Cartesian coordinate system of position vector is given by r equals to xi, yj, and zx. That means in three-dimensional, we can write this one. So the velocity can be written as velocity equals to derivative of the distance with respect to time. That means along the x-axis dx by dt and along the y-axis and along the z-axis will be dz by dt. So acceleration is also the same. So now what's the reference frame, the inertial frame and non-inertial frame? First of all, these are two types. One is inertial, one is and another is non-inertial frames. So inertial frame either in rest or moving with constant velocity, but in non-inertial frame accelerated frame. and unaccelerated frame. This can be also unaccelerated frame. But Newton's first law, that is law of inertia, does not hold here in non-inertial. But in inertial frame, first law, that means law of inertial hold. That means if acceleration equals to 0, then force will be 0. That is either sun lift either in rest or moving, okay, with constant velocity. But in first law of Newton's, acceleration not 0, where force equals to 0. For example, earth accelerated lift, etc. So this is the most important example for inertial and non-inertial frames. Now, the Galilean transformation. So what will be the Galilean transformation? Galilean transformation are used to transform Galilean transformation are used to transform the coordinate to transform the coordinate of a particle of a particle from one inertial frame to another. So relates that means the Galilean transformation are used to transform the coordinate of a particle from one inertial frame to another inertial frame. So let us consider two inertial frames. Let us consider S and S dash be two inertial frames where S being at rest and S dash moving with a constant velocity. Moving with a constant velocity. The constant velocity be relative to S. That means with respect to S. Let the position of two observer, let the position of two observer be at O and O dash. Observing the events, observing the events, at P. So we can, in that case, when the second frame moves relative to the first along the position, we can write like this. Suppose this is the first inertial frame, this is the y-axis, and this is the z-axis, and this is along x-axis. And another one, suppose another one is moving, and this is the z dash, and this is the x dash, and this is also y dash. So this is from at O, and this is at O dash. So at a constant velocity v, the position will be changed from O to O dash along the x-axis. So the point P, the point P, x, y, z, t will be transformed to P dash, x dash, y dash, z dash, and t dash. Okay. So we can write this, the Galilean transformation, as x equals to x dash. After moving with a constant velocity, we get x dash minus x dash will be what? The changed distance along x-axis will be x dash equals to x minus bt, and y dash will be y, and z dash equals to z, and t dash equals to t. So according to the Galilean transformation, we get this equation. Okay. So for the first case, we can say when the second frame moves related to the first along the position x direction, we get this one. Okay. So the equation transform to x dash equals to x minus bt, and y dash equals to y, z dash equals to z, and t dash equals to t. The same case, for the second case, when the second frame is moving along a straight line relative to first along any direction. So if the direction is any one, then along the x-axis bxt, okay, and distance will be bxt, and along the y-axis byt, and along the z-axis bzt. So in that case, the point position xyzt transform to x dash y dash z dash in this way. So the second frame s dash be moving relative to the first frame s with the velocity b dash. So b dash can be written as bxi plus byz plus bz for all directions. That means for three directions. In that case, the transformation of equation of frame s dash relative to s will be this: s dash equals to x minus bxt, y dash equals to y minus byt, and z dash equals to z minus z. So this is very easy for you. This is called actually Galilean transformation. So by equation 1 and 2 are called Galilean transformation equation. Let U and U dash be the origin of two frames S and S dash. Frame S dash moving with velocity B with respect to S. If R and R, the position vectors R and R dash, be the position vectors of an event P, then we can draw the inertial frames like this. So U dash will be transformed to U dash. Then the position will be changed along the z-axis. So then distance will be r equals to from the first one u dash plus u dash p. That means bt plus r. So r equals to r dash will be r minus bt, and t equals to time. So now an important question: Galilean transformation of a velocity and acceleration of a time. How we can calculate the velocity and acceleration of a particle with a Galilean transformation. Consider two identical frames S and S dash. The frame S dash moving with velocity v relative to S, which is given by this. So, and R dash be the position vector of the frame S and S dash. So then the Galilean transformation equation R dash equals to R minus Bt, you must know, and the time will be unchanged. So differentiating with respect to T, we get the differentiating the position vector R, we get the velocity. Okay, just and the time will be unchanged. Okay, so just putting the values we get, that means here by dt. So u dash is the initial velocity of frame S dash. So the velocity changed to u minus u dash equals to u vector minus, because the velocity measured by the observer in the two frames of reference are not same. So its inverse transformation form is can be written like this: u dash equals to u dash vector plus b. This is known as Galilean laws of addition of velocity. Similarly, if we differentiate the velocity with respect to time, we get the acceleration. Okay, so but acceleration will be not changed with respect to time. That is, the acceleration of both frames is invariant. That means independent or constant under the Galilean transformation. So we have to remember this one. Now, what will be the Galilean invariance? So according to it, the fundamental physical law and principles are well invariant under Galilean transformation. That is, the basic laws of physics are identical in all inertial frames of reference. So if we consider the laws of motion, that means Newton's laws of motion for frame S, that means force equals to just uh, rate of change of momentum. Okay, momentum means what? Mass multiply velocity. So we can write this equals to ma. But for another frame S dash, this will be changed to this. That means since acceleration are invariant, that means constant in Galilean transformation, so force will be also constant. So the force on the particle is invariant under the Galilean transformation. So very interesting one. Now laws of conservation of momentum. According to the law of conservation of momentum of Newton, you must know first momentum plus second momentum before and the after. So velocity will be changed. This is why momentum will be also changed. Uh, so now what's the Lorentz transformation? Consider two frame of reference S and S dash with U and U dash origin as origin respectively. Frame S is fixed. Frame S is fixed while another frame S dash is moving in position x direction with velocity v. That means parallel to x-axis. Okay. Consider two observe the events. Observe the events. That means light of signal that is produced for both the observe in both frames. So events P from S and S dash. So two observer observing these from position P. This is the position P. Events P. So position events P. So in figure we can write this one. So the equation can be written as the equation, the position vector, this P, X, Y, Z, and T transform to X dash, Y dash, Z dash, T dash. Okay. So here actually X equals to X dash equals to X minus BT, and Y dash equals to Y minus Y, and Z dash equals to Z, and T dash equals to T. So according to the Lorentz transformation, uh, we can write this equation. So according to the Galileans, we can write this one. But the Lorentz transformation, there are four types of equation we have to find out from the Galilean transformation. So from the Galilean transformation, we can find there are four types of equation. One is this: x dash equals to x minus bt root over 1 minus b square by c square, and y dash equals to y, z dash equals to z, and also t dash equals to t dash equals to t plus bx by c square divided by root over 1 minus b square by c square. So these four equations known as Lorentz equation. So here the according to the Lorentz transformation, we can write we get this one. Okay, but the if we write the inverse Lorentz transformation, then it will be for inverse one, this will be plus. Just this will be plus. So for only Lorentz transformation, this will be minus x minus bt and t minus bx by c square. Okay. So for inverse, we just adding plus. This is the inverse Lorentz transformation. This four equation. You have to remember this. So we can derive the Lorentz transformation equation easily by using Galileo's transformation. Okay, this is the actually reference frame for two observer. And according to the Galileo's transformation, you must know x dash equals to k into x minus bt. So here k equals to a proportionality constant, and its inverse transformation will be what? Just adding plus. And y and z will be invariants, that may not will be changed. So substituting the values of x dash from equation 1 in equation 2. Okay, just substituting this value, we get this one. Okay, now multiplying k with k square x minus bt plus k b t dash. So k b t dash equals to x minus k square x minus bt. Then t dash equals to what? Equation number 3. Also, the position of the light signal as seen from S and S dash for the two observer position is given by x equals to ct. C is the velocity of light and t is the time taken. So x dash equals to ct dash, because on light of velocity will be same. Now just k into x minus bt equals to c into what will be? Just putting the value of x, c into t dash equals to what will be? 3. From equation number 3, we can just put in equation 5. So we get after after multiplication with c, we get k equals to this one. So k equals to, so this equals to ckt and bkt. Now x equals to, we get ckt plus bkt divided by k minus 1 minus k square by kb into c. So from this line, we can write equation number 6. On comparing with equation 4 and 6, we get ct equals to this one. So from here, we get this one 1 by k square c by b equals to this. So 1 by k square c by b equals to this one. That means k equals to constant, proportionality constant equals to 1 by root over 1 minus b square by c square. So substituting these values in equation 1, we get x dash equals to this one. That means first equation. and substituting this values in equation number 3, we get t dash equals to this one. Okay, so just simplifying, we get t dash equals to, that means fourth equation of Lorentz transformation equation. So this equation is fourth one. Hence, we get the complete form of Lorentz transformation equation: x dash equals to x minus bt, we do root over 1 minus b square with c square, y s and z will be invariance transform, and t dash time dimension will be t minus bx by c square root over 1 minus b square by c square. C is the light, velocity of light, and b is the velocity of object. So this is the derivation of Lorentz transformation equation. And in inverse will be what? Just adding plus x plus bt, and this will be t plus bx by c square. Same definition, inverse Lorentz transformation. So now another equation, another question, show that the low value of velocity v Lorentz transformation approaches to Galilean transformation. The Lorentz transformation equation, you must know, we have derived this four equation. Since the velocity of object is more and more less than the velocity of light, so b by c tends to 0. That means this ratio will be tends to 0 because denominator is very larger. This is why the fractional value will be negligible. So from this above equation, we can write x dash equals to x minus bt, y dash equals to y, and z dash equals to z, and t dash equals to. So which is Galilean transformation. Hence, for the low value of velocity of object, Lorentz transformation approaches to Galilean transformation. So very easy for you. Okay. Now, what will be the length contraction? Actually, the length of moving rod is contracted along the direction of motion by a factor root over 1 minus b square by c square. So a moving object like aircraft or aeroplane or any aircraft of space or any rod you can consider appears to be shorter in comparison to its original length is called the length contraction. Suppose original length is L naught. So the contraction length will be capital L. So that means contraction length, shorter length will be LS. Then we get this relationship. Now we'll try to derive this one. How we can get this. So now we'll try to derive the length contraction equation. So consider two frame of reference S and S dash, and frame S is fixed while S dash is moving towards the positive direction of axis, towards the positive direction of x axis. Now we can figure out this actually like the previous Lorentz transformation figure. So this is the y-axis and this is the z-axis, and this one is also x-axis. So suppose there are two positions. This is the x1 and this is the x2 for the observer O. Now another frame of reference is moving towards the x-axis. So this will be, this is the S frame and this is the S dash frame. So this is the y y dash and this is the z dash. So now we'll try to calculate the length after moving. Okay. Now we'll try to find out, this is the original length, and original length will be what? L naught. original length. So, and moving length will be, and moving length of the aircraft or rod will be L naught. Okay, this is the moving and this is the at rest. Okay, so original length will be, sorry, this will be L naught and this will be LS, shorter length. Now we'll try to find out the so from this figure we can derive the equation. From this, if L naught and LS be the proper and improper length, or shorter length of the rod, then we can write we can write T naught equals to x2 dash minus x1 dash, and for the frame S, x2 minus x1 will be T. Sorry, this will be length L net, and shorter length will be x2 plus x1. This is the original length and this is the shorter length. This for S dash frame and this for S frame. Okay. Now by Lorentz transformation, now by Lorentz transformation equation, we get the fourth equation. The fourth one will be what? X equals x1 equals to, for the first frame, you can write x1 dash plus dt dash divided by root over 1 minus b square by c square. Lorentz inverse transformation. Remember it. Lorentz inverse Lorentz inverse transformation equation. So for the first one, x1 equals to this, and x2 will be what will be x2 dash plus b t dash divided by root over 1 minus b square by c square. So therefore, real length L naught equals to what will be? Real length L naught equals to, from this equation number 1, 2, and this is equation number 1. So from 2, L naught equals to what will be? X2 minus x1. Just putting this value, we get what will be x2 dash plus bt dash root over 1 minus b square by c square minus x1 dash plus bt dash root over 1 minus b square by c square. So taking LCM, we get x2 dash plus x1 dash taking LCM, we get this one. This divided by root over 1 minus b square by c square. So this will be x2 minus x1 dash. So L naught equals to this one, or from equation 1, we can write L naught equals to, this is the LS, shorter length, and this is the or moving length, root over 1 minus b square by c square. So from this equation, we can write LS equals to shorter length equals to original length root over 1 minus b square by c square. This is our required length contraction equation. Okay, length contraction equation. Very easy for you. Hope everybody will understand this. So we can say actually with the increasing velocity b, the length L decreases. Thus, the length of rod related to frame S appears to be shorter in comparison to the length of related to S dash. This is called length contraction. So now a real life example, when a rocket is moving with velocity 0.6 c, c means the light of velocity, that means 0.6 times the velocity of light, then how much contraction of its length? We are given velocity equals to what? 0.6 times the light of velocity. We know the length contraction will be original length root over 1 minus b square by c square. That means b means velocity of that objects and c is the velocity of light. So L by L not equals to this one. Just putting the velocity of b, we get this one. So the value will be what? L equals to 0.8 L by L naught. The ratio will be this. So 1 minus L by L naught equals to this. That means 20% shorter. Okay. Now, how first put a rocket to go relative to an observer for its length to be contraction to 99% of its the length at rest. That means length shorter length equals to 99% compared to original length. Okay. So L by L naught equals to what? 99 by 100. Now we know from the length contraction equation, shorter length equals to original length multiply root over 1 minus b square by c square. So L by L naught equals to root over 1 minus b square by c square. Then just putting these values, we can find out the relation. Okay. So b square by c, b by c equals to what? 0.141. So velocity equals to what? 0.106 multiplied with velocity of light. Velocity of light equals to what? 9 into 10, 3 into 10 to the power 8 meter per second. Now calculate the percentage contraction of rod moving with a velocity 0.8 times the velocity of light in a direction inclined at an angle 30 degree or 60 degree, anyone. Okay. Now you must know this is the original length. Okay. Original length in inclined in 60 degree. So along the base, the length will be L naught cos 60 degree, and along the perpendicular L naught sin 60 degree. So B equals to 0.8 times the This is given 0.8 times the light of velocity of light, and angle equals 30 degree. So shorter length equals to real length multiply cos theta along the x base. So we get the result, this one. Similarly, Lx, this is the r for the r position. This is the for x coordinate x axis along the x axis. We get this one. So we can calculate the length contraction along the x axis and y axis. Then the appeared length will be L equals to root over what will be length along x axis square plus length along y axis square. Just putting the values, we get the value of L. So from the equation, we get the now we can also get the observed length. So by comparing, we get the percentage 30%. Now we'll try to understand what will be the time dilation. First of all, what is the time dilation? Okay, a moving rock appears to be slower in comparison to clock at rest. That means there are two types of clocks. One is moving clock and another is in rest clock. So moving clock appears to be slower in comparison to a clock at rest. This implies that the moving clock appears to go slow. The effect is called time dilation. So what is time dilation? That means moving clock appears to be slow. So let a a clock is fixed in the moving frame on observer in S dash finds that the clock produces two time T1 dash and T2 dash. The time interval between these ticks in the frame S dash is which is moving reference is given by T naught equals to what will be T2 dash minus T1 dash. So from the inverse Lorentz transformation equation, we can write T1 equals to what? T1 dash plus Bx by C square divided by root over 1 minus B square by C square. And T2 for the time 2 from the second tick, T2 equals to this will be T1 dash and this will be T2 dash. All are same. So from this, just putting the values, we get what will be. Now just subtracting T2 minus T1 will be what? This one. Okay. So T2 minus T1 will be T2 dash minus T1 dash divided by root over 1 minus B square by C square. But T2 minus T1 equals to what? T, original time. This is the time, second time, time for the reference S. But for the reference, moving reference, T naught equals to T2 minus T1 dash. So from this, we can write small t equals to T naught divided by root over 1 minus B square. Thus, a clock appears to run to its faster rate when it is at rest relative to the observer and appears to be slower by factor. Slower how many times? Root over 1 minus B square by C square when it moves. But you must know velocity v is more and more less than the velocity of light. So if time t is infinite, that means if time is not fixed, then that means the time does not changing and the age will not grow. It is never possible. So time cannot be infinite because age will be not grow. Now we'll try to understand a very important uh, part, twin paradox. To explain the twin paradox, suppose there is a pair of twins. One is Sita and Gita. Okay, if Sita stays at Earth and Gita goes on a trip to a planet in a high-speed spaceship and returns back to the Earth, Gita will find Sita to be old. Thus, space traveling twin Gita, well, find herself younger than her twin sister Sita on return to Earth because Gita's heartbeat will be slower than Sita's heartbeat. So this is called actually twins paradox. If TS, if the time passing for the Sita and time passing for Gita will be capital T with the ages of Sita and Gita. So by the equation of time dilation, so time dilation we can write Tz for Gita's time is equals to Sita's time is divided by root over 1 minus b square by c square. That is Gita time will be greater than Sita. Now we'll try to solve some real life example. At what speed should be a clock be moved so that it may appear to lose 4 minutes in each hour? That means 4 minutes in each hour. 1 hour means what? 60 minutes. So time will be 60 minutes. And T naught will be 56 minutes. 60 minus 4. So from the equation of time dilation, we can write this one. Just putting the values. T naught by T equals to 56 by 60. We get velocity will be what? This one. 10.75 multiplied 10 to the power 7 meter per second. Now, at what speed a clock be moved relative to an observer so that it may seem to lose 1 minute per day? So 1 day means what? 24 hours. So 1 hour means 60 minutes. So T equals to what will be? 1440 minutes. And T naught will be because slower by 1 minute per day. This is why 1 for 39 minutes. T naught equals to 1 for 39. Now the speed of the observer B equals to, we get B equals to 1 minus naught by T whole square root over. So time dilation formula is given as this, but T naught equals to what will be speed of light, because the speed of clock is moved relative to the observer. So just putting these values, you can write this one. Fine. Result. Now the variation of mass with velocity. Consider two frames of reference S and S dash, look like Lorentz transformation. Frame S is fixed while the frame is S dash is moving along positive direction with the velocity p. So let two identical bodies A and B of masses m1 and m2 move with the velocity u dash and minus u dash. Okay, in opposite direction to each other. It's u and u2 will be the velocities of the bodies related to the frame is S. So figure can be drawn like this. This is the first observer and this is the second observer. So position is the S frame and is the S dash frame. So S dash frame is moving along the x-axis. So suppose there are two bodies at A and B. One A bodies with mass m1 and B bodies with mass m2 meeting each other. So then u1 is velocity of the first order, first one. So and u1 equals to, from the Lorentz transformation, we can write this one. Now the for the first velocity u1 equals to, we can write this one, and for the u2, for the second one, second velocity, the direction will be minus u1 dash. So after collision, they coalesce. Then from law of conservation of linear momentum, we can write this. Okay, substituting equation 1 and 2 in equation 3, we get this one. So after simplifying, we can find m1 into this and m2 into this. So new denominator is this, just omitting the numerator, we get this one. Now from equation 1, we get u1 equals to this, from inverse Lorentz transformation. Squaring and dividing by c square and substituting, subtracting from 1, we get this equation. So after simplifying, we get the this result. So on dividing equation, and similarly from equation 2, we get minus 1 minus u dash b divided by c square root over this one. So this is equation number 6. Now from dividing equation 5 and 6, we get equation number 7. So comparing equation 6 and 7, 4 and 7, we get m1 divided by m2 equals to this one. Now, if the velocity of second object's mass m2 will be 0, then we get m1 equals to m2. But m1 by m2 can be written as 1 by root over 1 minus b square by u1 square by c square. So m1 equals to m0 divided by root over 1 minus u1 square by c square. So there is a relationship between two masses. So we can conclude that using the common notation, if first mass, the mass of first object will be m and velocity u1 equals to b, then we get the, so original mass m0 cannot be changed with the velocity b, but the moving mass will be decreasing. So we get m equals to m0 divided by root over 1 minus b square by c square. So this is the relativistic formula for the variation of mass with velocity. This implied that the mass of a body increases with the increasing its velocity. If the velocity is increasing, then mass will be increasing. So it's a very interesting for relativity, special relativity. For special cases, we can write if the velocity of objects of mass m vary and more less than the velocity of light. So we can omit the ratio b square by c square, which tends to 0. So in that case, we can write m equals to m0. That means the mass will be not changed. If the velocity of objects is more and more less than the light of velocity, in that case, mass will be not changed. So this is the special condition for this. So if the velocity tends to velocity of light, that means the moving velocity of object is the same as the light of velocity. So in that case, b square by c square equals to 1. So in that case, mass will be infinite, which is not possible. Which means that if a material of particle travels with the speed of light, its mass and hence energy would become infinite. And this is not possible because mass can never be infinite. Thus, it is impossible for a material particle to move faster than the speed of light of space. So why it is not possible to move for a particle to move the faster than the speed of light? This is the example for that. Now we can solve some uh, real life example. Uh, Deduce the velocity at which the mass of the particle will be 5 times the mass of rest at rest. So we must know m equals to m0 divided by root over 1 minus b square by c square. So given that mass equals to 5 times the mass at rest. So the rest at mass mass will be m0. This is what m equals to 5 m0. So velocity of light will be this 3 into 10 to the power 8 meter per second. Now just putting the values, we can write, we get the velocity b square by c square equals to this one. So b equals to will be 1.2 into 2.9 into 10 to the power 8. So velocity will be 2.978 into 10 to the power 8 meter per second. So very easy example. Now mass and energy equivalent relation. You must know the mass if the velocity of object travel with the with the light of velocity, then mass transform to energy. So this is very special equation for Einstein, uh, the mass energy equivalence relation. That means equals to mc square. So consider a body of mass m moving with velocity b. Then from the relation we can write this. So mass equals to original mass divided by root over 1 minus b square by c square. So small m is the moving mass. So m square equals to, just squaring on both sides, we can write this one. So m square, c square, just taking LCM, c square minus b square divided by c square. Now m square into c square minus b square equals to m naught square into c square. So we get m square c square minus m square b square equals to m naught square into c square. Now differentiating with respect to m on both sides, c square, m square x square formula twice x, okay, but it is not original x, this is why dm minus, and b square will be constant because the differentiation is there is with respect to m. So b square 2 into m, twice m square means was twice m dm. So equals to m naught square, uh, original, m square twice b db. Here actually UV process, you are using UV process, u into, that means b square into m square differentiation, my plus b square, uh, m square into b square, b square differentiation. B square differentiation was twice b db. So plus minus minus. This is the original mass. Okay. This is constant. This is why 0. Okay. And velocity of light also constant. This is why 0. Now right hand side is 0, as both these are constant because m naught is the original mass of the objects and c is the velocity of light. This whole constant. This is why differentiation with respect to variation, uh, uh, variate mass will be 0 because m is the variable mass. Okay, variable changing mass with the velocity, and b depends on the mass. This is why b is also variable here. Now after this line we can write twice m c square dm minus b square, just taking twice m common. Then since this m is not equal to 0, so 2 is also not equal to 0. This is why dividing by twice m on both sides we get this line. Now c square dm equals to b square dm plus m bdb. This is equation number 1. Now from work energy theorem, you must know the total energy. Energy will be total work done. Total work done. So total work done will be for the for small energy and a small work done. So work done equals to what? Force multiply displacement. Okay, this is equation number 2. You must know force equals to what? Rate of change of momentum, and it's from Newton's second law of motion. So we get ddt is to mb, where momentum equals to mp equals to mb. Now force can be written as, this is the UB process in differentiation with respect to time, u into dB dt plus b into dm dt, just UB process of differentiation. Now thus from equation 2, just equation 2, the dk equals to value of f into ds. So m dB dt ds multiplication. Okay. Now m ds dt dB plus b, just ds dt into dm. So ds by dt means you must know this is the velocity formula, and this is also velocity formula. So dk, energy equals to mb db plus b square dm. This is equation number 3. So from this equation, we can write, on comparing equation 1 and 2, we get, uh, comparing equation 1 and 3, we get kinetic energy equals to c square into dm. Now to find out the total kinetic energy, we have to integrate with respect to k, 0 to k. Okay. At rest, before moving, the energy will be 0, but after moving, the highest energy will be k. So dk, and c square dm. Your original initial mass will be m naught, and final mass will be m. So dm, just we get 0 to k, just simple integration. K equals to total energy equals to mc square minus m naught c square. So total energy equals to what? Kinetic energy plus potential energy. You must know total energy can be measured by this equation. So kinetic energy mc square and minus m naught c square. But potential energy equals to what? Mass at rest multiply c square, velocity of light square. So this and this will be cancelled. We get equals to mc square. This is Einstein's mass energy equivalent relation. This implies that with the increasing energy of a particle, its mass increases. Thus, a hotter body have a greater mass to colder body. So this is the real life example of this. So this is the mass energy equivalence relationship. Now, relation between relativistic momentum and energy. From mass energy equivalence relation equals to what? mc square. But we know from mass variational mass equals to original mass divided by root over 1 minus b square by c square. So equals to, we can write, mm, just putting these values. So, but momentum equals p equals to mb. Okay, b equals to momentum divided by m. So E equals to can be written as m naught c square divided by root over 1 minus, just putting the value of b here. Okay, b equals to what? P by m. Just putting this one equals to m naught c square divided by root over this, and equals to this one. So after this line, we can write p square equals to this one. So by cross multiplication, we get this. So E square equals to E square minus P square C square equals to M naught square C to the power 4. So where C is the velocity of light, M naught is the original mass of the object, and P is the momentum of the objects after velocity of C. So this is the required relation between relativistic momentum and energy. Now, relation between relativistic momentum and kinetic energy. So you must know from this E square equals to minus P square C square equal to M naught square C to the power 4 from this one. Okay. So E square equals to this one and equals to root over this whole. Since the total energy equals to kinetic energy plus rest mass energy, that means potential energy. So equals to K into M naught C square. So equals to this one. Now just calculating, we can write this one. So this is required relation between relativistic momentum and kinetic energy. Very easy relationship. Now, particle with a zero rest mass. Photon is a particle with a zero rest mass, and the main properties of photon are the mass and momentum of photon. You must know kinetic energy of mass of photonic m equals to mass of photon will be what? E by c square. So m equals to s nu by c square. So we can write m is proportional to nu, and the momentum of photon equals to mc. But you know, momentum equals to mass multiply velocity. So just putting the values, we get momentum is proportional to 1 by lambda. The existence of photon was given by photoelectric effects and quantum effect experiment. The energy of photon, the energy of photon was derived by the Max Planck by relation equals to h nu, where s is the Planck constant and its value is 6.63 into 10 to the power minus 34 joule per second. The energy of the photon is measured by the electron volt. One electric volt equals to 1.6 into 10 to the power minus 19 coulomb. Now, some important example related to it. A particle of rest mass m naught moves with the velocity 0.6 times with the velocity of light. Where c is the speed of light? Calculate its momentum, kinetic energy, and total energy. So, given uh, velocity of object equals 0.6 times rate of velocity of light. So, rest mass equals to m naught. We must know moving mass equals to rest mass divided by root over 1 minus b square by c square. So just putting these values, we get m equals to 1.25 times m naught. So you must know momentum equals to p equals to mb. So p equals to just putting the values, we get this. And total energy equals to mc square. Just putting these values, we can write 11.25 m naught 10 to the power 16 meter square second square. And total energy, rest mass energy plus kinetic energy. So total energy equals to this. Very easy one. Now a particle has a velocity equals to 3I plus 4J plus 12K meter per second. And this is the velocity. So the moving with the velocity 0.8 times the velocity of light related to laboratory along x-axis direction. Find the velocity of u in laboratory frame reference. So given u equals to this and ur position will be 3 along the x-axis and along the y-axis 4 units and along the z-axis 12 units. So velocity of light equals velocity of what? 0.8 times the velocity of light. So just putting in the Lorentz transformation equation, we get the ux equals to this and ui also this. Okay, very easy. Just putting the values, we get the velocity of the laboratory frames. Now concept of ether. Ether is a hypothetical medium, exists everywhere, even in vacuum. It have a very large elasticity and very low density. The relative motion between the earth and light does not affected by ether. Thus, ether provides a fixed frame of reference relative to which the speed of light is the same in all direction. Now another example, find the percentage contraction of 1 meter rod moving with a velocity of 0.8 times the velocity of light inclined at 60 degree to own its own length, where c is the light of velocity. We are given b equals to 0.8 times the light of velocity and angle will be 60 as the previous example. Okay, very easy for you. This contraction will be 30%. And calculate the effective mass of a photon of wavelength 1 angstrom. Okay, so given lambda equals to what? Effective mass will be 1 angstrom. That means angstrom means 10 to the minus 10 meter. Velocity of photon will be velocity of light. So de Broglie's equation lambda equals to h by mb. Just putting the values, we get the mass. Find the rest mass energy of an electron whose rest mass is m naught equals to this. Rest mass energy of electron is given by this 9.1 into 10 to the minus 31 kilogram multiply with the velocity of light. Okay, whole square equals to mc square. Okay, just using this one, we can write. You get the now calculate the mass of a particle moving with velocity equal to 0.9 times the velocity of light. Where is the velocity of light and its rest mass is 9 m naught equals to 9.1 10 to the minus 31 kilogram. So the relativistic mass of the particle, you must know this relation. So moving mass equals to what is rest mass divided by 1 root over 1 minus b square by c square. Just putting these values, you get the result. Very easy for you. So this is the mm, so in short, actually, we have discussed about the special theory of relativity, what are the frame of references, definition of frame of reference system of coordinate axis which defines the position of a particle in two or three-dimensional space is called frame of reference. So there are two types of frame of references: inertial frame of reference, and other is non-inertial frame of reference. And Galilean transformation, we have also discussed about this. If events p like this, we also what is ether, we also discussed the what is ether. The wave nature of light seem to be unique propagation medium, it is called ether. Okay. Mm, Now the Michelson's Morley experiment to find out the ether. Now there are two types of mirror, m1 and m2 are placed at pm1 equals to pm2. Okay. Now in time tree 2, the mirror m1 shifts to m1 and travels a distance bt2, because distance equals to velocity multiplied time. So the Michelson Morley experiments, if light requires a medium, then its velocity depends on the velocity of the medium. So velocity vectors add. So parallel velocities, velocity of light and velocity of ether will be added. So total velocity will be these two, sum of these two. And anti-parallel velocity will be velocity of ether moving towards the velocity of total velocity, then we get the velocity of light. So in that case, total velocity equals to velocity of light minus. So post, so we can describe the experiments. Mm, we can define the experiments, Michelson's Morley experiments. So a number of experiments are performed to detect a relative motion between Earth and ether. But the most famous among them is one of the performed by the Michelson Morley in 1887. The experiment arrangements, the Michelson Morley experiment mm, uh, of two excellent optically plane mirror M1 and M2 in our previous figure, two plain glass plates P and Q of equal thickness and of same materials. Plate P is semi silvered glass plate while plate Q is transparent. They kept at 45 degree to the interferometer arms. A telescope capital T is used to observe the fringes. Okay. Now the figure will be like this. Okay. So there will be two mirror M1 and M2. And so this is the source and P are Q. The two. Uh, so and M1 and M1 dash. This is the image. And M2 will be another mirror. Now consider two mirror M1 and M2 be at equal distance from the plate P. That is PM2 equals to PM1 equals to L. We can consider this. Say. Let C and B be the velocity of the light and apparatus respectively. C is the velocity of light and B is the velocity of apparatus. Now using the geometry in triangle PM2 dash Q dash we get. So PM2 dash Q dash, this is the P and this is the M2 dash and this is the Q2 dash. Okay. So from by geometry, PM2 dash and Q dash will be, we get the total path transversed by reflected beam will be PM2 dash Q dash equals to PM2 dash plus M2 dash Q dash. So this equals to actually PM2 dash equals to M2 dash Q. This is why this can be written as 2 PM2 dash. Now, now PM 2 dash whole square equals to PU square plus QM2 dash whole square. Since P equals to BT, distance, travel distance BT, and QM2 dash equals to L. Okay. Now PM2 dash equals to CT, velocity for light. Thus, by Pythagoras theorem, C square T square equals to B square T square plus L square. Now T equals to T divided by root over C square minus B square. Now, if T1 is the time taken by reflected ray to travel total path, T1 equals to what will be twice time T to multiply this. Thus, T1 equals to 2L by C, this one, root over 1 minus B square by C square to the minus half. So, T1 equals to this one. And the total time taken by the transmitted wave and reflected wave from P to M1 and M1 dash to P. This is the time taken. Now, T2 equals to this one. So, T2 equals to we get this one, B me cut. So, T2 equals to finally we get twice L divided by C multiply 1 minus, sorry, 1 plus B square by C square. So, the time difference will be difference time delta equals to T2 minus T1. Just putting the value of T1 and T2 here, we get time difference what? L B square by C cube. Okay. So, time difference, thus the path difference or time difference, it is the path difference equals to C del T. Okay. C del T equals to what was? L B square by C cube. So, del equals to L B square by C square. CC cancel. So, if the whole apparatus is turned through 90-degree angle, then the fringe shift will be del equals to L B square by C square equals to N lambda. So, N equals to L B square by lambda C square. In Michelson Morley actual experiment, length was 11 meter, B equals to velocity was 3 into 10 to the power 4 meter per second, and lambda equals to was 5.5 in 5.5 angstrom, that means 5.5 10 to the power minus 7 meters, C equals to 3 light of velocity. So therefore, N equals to L B square by lambda C square. So from this experiment, N equals to, just putting the given values of Michelson Morley, we get N equals to 0.2. So this displacement of fringe could be detected by Michelson Morley apparatus, but this fringe shift was not observed. This indicates that the relative velocity between Earth and ether is zero. That means there is no ether. So explanation of the negative result, ether drag hypothesis. The moving earth drag the ether along with it, and hence there is no relative motion between the earth and the ether because there is no fringe shift was observed. So Lorentz Fitzgerald contraction hypothesis also shows that offered a suggestion for this. The suggestion was a material body moving through other ether, moving through ether is contracted in the direction of a motion by effect of this. So this is actually using length contraction. We also he also observed that Michelson Morley experiment observed no contraction in length because there is no fringe shift. So consistency of speed of light. The proper explanation of null result of Michelson-Morley experiment was given by Einstein. He proposed that the speed of light is invariant. That means they are constant. So the speed of light is constant and does not depend upon the motion of the source. So this is actually a result of Michelson-Morley experiment. So postulates of special theory of relativity. Then we observe two postulates, and we also discuss that Lorentz transformation, Lorentz transformation, and we also discuss the difference between Galilean's transformation and Lorentz transformation. So we have observed this, and we can also derive the Lorentz transformation. So length contraction, we also discuss the length contraction, and also time dilation, definition of time dilation, we also discussed this, and velocities addition, just adding velocities components along the x-axis ux equals to this, and along the y-axis velocity this, along the z-axis velocity. So for the moving reference, ux dash uy dash uz dash will be this. So from the inverse Lorentz transformation, the equation will be changed. Okay, very easy. The variation of mass and velocity, we also discussed this, and also derive the relationship between original mass and the moving mass. And we also discussed Einstein's mass energy relationship and derived it also. Okay, so that means equals to mc square. We also derive energy momentum relations. This one we can, that means the in limit of a small velocity, the relativistic relation between kinetic energy and momentum tends to the classical relationship. Now what is the classical relativity? Actually classical relativity, if we suppose there are 10 lakh meter per second velocity in an aircraft, and another one is 1 lakh, 10 lakh, one, 10 lakh, and this is 100, 10 lakh meter per second. This is also 10 lakh per meter per second, their velocity. So this is the example of classical relativity. Classical relativity shows they are moving, and how fast is a spaceship approaching a spaceship B? How fast? That means how fast both spaceships see the other approaching at 220 lakh meter per second. So this is the classical relativity. Okay. Now, so Einstein's special relativity, what's the says? Suppose one is not moving, so 0 meter per second, and the first space shift 10 lakh meter per second, and another one is uh, one 30 crore, okay, meter per second. So if they move to each other, then what will happen? Both spaceman measure the speed of approaching ray of light. How fast do they measure the speed of light to be? Actually, stationary man will be measured 3 lakh meter per second. The man traveling at 10 lakh meter per second will be 3 crore 10 lakh. Okay, and wrong. So the speed of light is the same for all observer. This is called the Einstein, which is called the special theory of relativity. Okay, so time travel, time between ticks equals to distance by speed of time. So if there are two clock, so one clock is moving in one direction, another clock is it at rest. So light in the moving clock covers more distance. Okay, so but the speed of light is constant, so the clock ticks the slower. Understand? Uh, so moving clock run more slowly. So three strange effects of special relativity, which we have discussed here: Lorentz transformation, relativistic Doppler effect, headlight effect. Now, Lorentz transformation we have discussed. This is the actually where observer watching the actual length. So original will be this, and this is the okay. So light from the top of the bar has further to travel. Is therefore takes longer to reach the eye. Okay. So the bar appears bent. That means shorter length. Okay. So Doppler effect, what will be? A car is moving and the pitch of the siren uh, rises as the ambulance approaches, falls once the ambulance has passed. The same applied to light. Okay, electromagnetic spectrum. So this is called actually Doppler effect. Doppler effect. And approaching objects appear blue shift, and receding object appear red shift. So headlight effects. This is the light of torch, coming light from it. So if the velocity is v and shorten, okay, so beam becomes focused. The same amount of light concentrated in a smaller area. In initial stage, the yeah, it was in big area. Then after shrinken, the velocity beam becomes focused. The same amount of light concentrated in a small area. Torch appears brighter. So program used to visualize the three effects. Okay. Fun, sun stuff. So this is called actually, this is the classical relativity. So after Michelson Morley result, uh, and the Maxwell's equation also predicted the speed of light is constant in any reference. So this is famous, poor famous equation of Maxwell's integral in integral form, and velocity of light 3 into 10 to the power 8, where the speed of light is given through the constants from both electricity and magnetism. So Albert Einstein in 1905 published 4 papers, 2 on special relativity, in 1916 published about general relativity and search for a unified theory. So this is the main postulates of relativity, principles of relativity, and this one. So we have discussed about this in our entire class. We also discussed the time dilation. This is we also discussed about the twin paradox situation, that experiment involving a set of twins, speed and gas flow. The speed of travels to a planet X 20 light years from Earth. His ship travels at 0.95 times 0.95 times to the velocity of light. After reaching planet X, he immediately returns to Earth at the same speed. When Speedo returned, he has aged 13 years, but Gaslu has aged 42 years. So this is the twin perspectives. So you can calculate this one. This is the time dilation, length contraction also. We also discussed this equation. We also discussed this one. And energy relativistic momentum, we also derive this formula. Black holes. Okay, thanks to everybody. I hope you will enjoy this class, theory of relativity. So best wishes to everybody. Thanks to everybody.